Right now, as you listen to these words, the most distant object ever created by humanity is crashing into something that should not exist. A wall, an invisible, colossal, impenetrable structure at the very edge of the solar system. And nobody, absolutely nobody, can explain why it is there. Imagine two small spacecraft launched in 1977, flying through the void for almost half a century. They crossed the orbits of all the planets, passed the gas giants, moved beyond the Kuiper Belt, and rushed to where no human instrument had ever looked, to the very frontier of our stellar home. And there, at a distance of more than 20 billion kilometers from Earth, Voyager discovered something strange. The data it sent back forced scientists to fall silent because there, at the edge of everything we know, space behaves as if it hits a barrier, as if something will not let it go further, as if someone or something drew a line and said, "No further." And this is only the first of three mysteries we will reveal today. The second is the mystery of temperature. At the border of the solar system, a zone was recorded where the temperature of the space environment suddenly rises, not by 1 degree, nor by 2. The interstellar plasma in this region is heated to 50,000 degrees. In a place where, by all calculations, absolute cold should reign, there exists an invisible hot barrier. Where does this energy come from? What feeds this impossible heat in the deepest void imaginable? And the third riddle, the most disturbing one. The magnetic field outside the heliosphere turned out to be completely different from what the models predicted. Its direction, its strength, its structure. Everything turned out to be wrong, as if our solar system is floating through something we completely do not understand, something that deforms the very space around us. Something we did not even suspect until a small craft weighing just over 800 kilograms reached the edge and looked beyond it. Tonight you will learn what will keep you awake, or, conversely, take you into such depths of reflection that you will not want to return. We will talk about the wall at the edge of the solar system, about what Voyager found where there should be nothing, and about what it means for each of us, for every living being on this small blue dot drifting in infinity. If you are fascinated by the mysteries of space, subscribe to the channel. This journey begins right now. Let's start with what we thought we knew, with the version of reality we were told in schools, in popular science books, in documentaries, a version that seemed coherent, logical, almost complete. And then let's see how Voyager smashed it to pieces. So, the official picture. Our solar system is the sun in the center, 8 planets rotating around it, the asteroid belt between Mars and Jupiter, and the distant Kuiper belt beyond the orbit of Neptune, where icy bodies, dwarf planets like Pluto, and billions of frozen debris reside. Beyond the Kuiper belt is the Oort cloud, a giant spherical shell of trillions of comets extending perhaps 1 light-year from the sun. And beyond that is interstellar space, void. Nothing. Just an endless vacuum until the next star. A beautiful picture, simple, clear, and absolutely wrong. Because between the Kuiper belt and interstellar space, there exists something that was talked about in passing for a long time. The heliosphere, a bubble, a giant cocoon of charged particles that the sun blows out with its solar wind. This bubble extends for billions of kilometers in all directions, and it is what defines the true boundary of the solar system. Not the orbit of Pluto, not the Kuiper belt, but the heliosphere, because inside this bubble, the laws of our star operate, its magnetic field, its flows of particles, and outside its borders, the territory of the galaxy begins. Different rules, different forces, a different reality. And it was exactly at this border that Voyager discovered a wall. Well, let's go in order. To understand what happened, one must understand how Voyager even ended up where it did, and why its discovery overturned our understanding of where our home ends and foreign territory begins. 1977, the United States, Cape Canaveral, Florida. On August 20th, Voyager 2 launches from the spaceport. 16 days later, on September 5th, Voyager 1 follows. Yes, that is not a typo. The second was launched first. It is just that Voyager 1 flew a faster trajectory and overtook its twin while still on the way. Both crafts were designed for one main goal: the study of the outer planets of the solar system: Jupiter, Saturn, Uranus, Neptune. Their mission was supposed to last 5 years, maybe 10. No one seriously expected that these small crafts, powered by radioisotope thermoelectric generators on plutonium-238, would work for half a century. No one dreamed that they would reach the edge of the solar system. It was beyond imagination, but they reached it. Voyager 1 completed its planetary mission in 1980, flying past Jupiter and Saturn. Voyager 2 in 1989 after meeting Uranus and Neptune. And after that, both crafts began their long journey away from the sun, into the void, into the unknown. Years passed, decades. The crafts slowly, at a speed of about 17 kilometers per second, that is approximately 61,000 kilometers per hour, moved away from us. Every day they covered about 1.5 million kilometers, and every day they sent data back to Earth. The signal from Voyager 1 takes more than 22 hours to reach us. Imagine that. You ask a question, and the answer arrives 2 days later. The power of the craft's transmitter is 23 watts. That is less than the light bulb in a refrigerator. And this whisper from the abyss is caught by the giant antennas of the Deep Space Network scattered across 3 continents: in California, in Spain, and in Australia. And this whisper began to tell us impossible things. The first signs of anomaly appeared back in the mid-2000s. Voyager 1 began to record changes in the environment. The speed of the solar wind, which had been blowing on the craft for 30 years, began to fall not gradually, but sharply in stepped jumps, as if the craft was approaching a certain wall, and the wind blowing at its back hit a barrier and slowed down. In 2004, Voyager 1 crossed the so-called termination shock, the point where the solar wind sharply slows from supersonic to subsonic speed. This happened at a distance of about 14 billion kilometers from the Sun, or 94 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers. Imagine if the Earth were 1 step away from the Sun, then the termination shock boundary would be 94 steps away. Far? Certainly. But Voyager was already there. After crossing this boundary, the craft entered a zone that scientists called the heliosheath, a transition region between the inner part of the heliosphere and interstellar space. And here the most interesting part began. The heliosheath turned out to be completely different from how it was imagined. Scientists expected a smooth transition, a gradual weakening of the solar wind, and a buildup of the interstellar medium. Instead, Voyager discovered chaos. Magnetic fields were intertwined, directions changed, creating vortices and bubbles. Charged particles behaved unpredictably. The temperature began to rise instead of falling. The density of matter fluctuated in jumps. It did not look like a smooth boundary, it looked like a wall, not a wall of stone or metal. Of course, space walls are not like that. It is a wall of energy, magnetic fields, and glowing plasma, but it is just as real and just as insurmountable as any physical barrier. And here is what truly shocked scientists. When Voyager 1 finally crossed the heliopause, the formal boundary of the heliosphere, in August 2012 at a distance of about 121 astronomical units from the Sun, the data became even stranger. The density of the interstellar medium turned out to be 40 times higher than models predicted. 40 times. This is not a small margin of error, it is a catastrophic failure of theoretical predictions. Scientists spoke at conferences and said, "We expected one thing, but we got something completely different. Our models do not work. We do not understand what is happening at the edge of the solar system." And that was only the beginning, because 6 years later, in November 2018, Voyager 2 crossed the heliopause at a distance of 119 astronomical units from the Sun, and its data confirmed and deepened the mystery. The wall exists. It was not a coincidence, not a malfunction of the instruments. Both crafts, crossing the boundary at different points in space with a difference of 6 years, recorded the same anomaly. Moreover, Voyager 2 had a working plasma detector, which on Voyager 1 had failed back in 1980. And this detector showed something amazing. The transition through the heliopause was incredibly sharp, not blurred, not gradual, but almost instantaneous. The craft literally crashed into a wall of interstellar plasma. In a matter of days, the characteristics of the environment changed radically. Let's break down what wall means in this context, because it is important. We are used to thinking of space as a void, as an endless nothing in which stars and planets float. But this is a fundamental misconception. Space is not empty. It is filled with gas, plasma, dust, magnetic fields, cosmic rays, flows of charged particles. The density of this matter is negligible by Earth standards, a few atoms per cubic centimeter, but on the scale of space, it plays a colossal role. And at the border of the solar system, this thin matter behaves like a wall. The solar wind, a stream of protons and electrons flying from the sun at a speed of 300 to 800 kilometers per second, hits the interstellar medium and stops. It cannot break through further. Like a river flowing into a lake, it spreads out, slows down, heats up from the collision. And it is in this collision zone that what Voyager recorded as a wall is formed. But here is what is inexplicable. This wall turned out to be much denser, hotter, and more structured than any model predicted. It turned out to be not a blurred cloud, but something that has a shape, has clear boundaries, has physical properties that do not fit into existing theories. And now, forget everything you heard before about a simple and clear solar system with neat orbits and predictable boundaries. Because the reality turned out to be much more complex, much stranger, and much more frightening. Think for a second. We live inside a bubble that our star blows out in interstellar space. And this bubble is the only thing that protects us from the full power of galactic cosmic rays, from interstellar radiation, from flows of high-energy particles that continuously bombard our cocoon from the outside. The heliosphere is not just an abstract boundary on a map. It is a shield, the only shield between life on Earth and the ruthless radiation of the galaxy. And now we discover that this shield hits a wall, something that presses on it from the outside, something that deforms its shape, compresses it, makes it vibrate and pulse. And we do not know how strong our shield is. We do not know if it can ever weaken. We do not know what will happen if the wall turns out to be stronger. This is not science fiction. This is data transmitted by real spacecraft from a distance of more than 20 billion kilometers. Data that forced scientists to rewrite textbooks. The official version that we understand the boundaries of our solar system crumbled, and in its place grew a mystery that becomes deeper with every new bit of information Voyager sends. But reality, as always, turns out to be much darker than we are ready to admit. Because the wall at the edge of the solar system is not just a physical phenomenon, it is a window into something greater, something that makes one think about the very nature of the space in which we exist, about the forces that shape our galaxy, about processes that can destroy all life in a matter of millennia. When NASA scientists analyzed the data from both Voyagers, they noticed a detail that at first seemed insignificant, but over time became the central mystery of the entire mission. The electron density in interstellar space did not just turn out to be higher than expected. It continued to grow as the craft moved away from the sun. This completely contradicted intuition. If we imagine that the interstellar medium is a homogeneous gas, then the density should be approximately the same in all directions. But Voyager 1, moving further away from the heliopause, recorded a steady growth in density, as if it were moving not into a void, but into something increasingly dense, increasingly saturated, as if it were entering something. In 2021, Voyager 1 data showed that the electron density in its vicinity reached record values, approximately 0.040 atoms per cubic centimeter. This might seem like a negligible number, but in the context of interstellar space, it is huge. This is 10 to 20 times more than expected. And here is what it means. The solar system is surrounded by something. Not a vacuum, not a void. Something. Dense, hot, structured, something that has a shape, direction, dynamics, something that presses on our cocoon from all sides. And we are only beginning to understand what it is. But before we move further, before we look into the very heart of this mystery, I want you to realize the scale. Voyager 1 is now at a distance of more than 160 astronomical units from the Sun. That is 24 billion kilometers. If you sat in a car and drove at a speed of 100 kilometers per hour without stopping for a second, it would take you 27,000 years to reach the place where this craft is flying now. 27,000 years. All of recorded human history is 5,000 to 6,000 years. Our entire civilization is only 1/5 of this path. And despite all this, Voyager has covered a tiny fraction of the distance to the nearest star. Proxima Centauri is 4.24 light-years away from us. It will take Voyager more than 70,000 years to reach it. It has not even covered 1,000th of that path. And yet, even at this tiny distance, it has already discovered something we are unable to explain. The wall at the edge of the solar system. A hot, dense, invisible barrier that surrounds our world. And the further we look, the more questions arise. Because if our solar system is surrounded by a wall, then what is behind it? What generates this density, this temperature, this structure? Where does the energy come from that maintains this barrier for billions of years? And the most important question, the most disturbing one. This wall, does it protect us or does it hold us back? We do not know the answer. Not yet. But Voyager continues to fly, continues to whisper its 23 watts into the abyss. And with every day, it opens another piece of the puzzle that may turn out to be the most important mystery in human history. Close your eyes. Imagine infinite darkness. Imagine a small craft the size of a passenger car rushing through this darkness at a speed of 17 kilometers per second. Its antenna is pointed at a tiny dot that has long ceased to be a blue sphere and has become just another star. Its instruments record every particle, every magnetic vibration, every echo of cosmic rays. And all its data says one thing. Ahead is a wall, around is a wall, everywhere is a wall. And now get ready, because in the next part, we will look inside this wall. We will break it down atom by atom. We will understand what it consists of, what forces create it, and why it may be not just a physical phenomenon, but a key to understanding the very structure of our galaxy. But be careful. The deeper we look into this secret, the more it looks into us. To understand exactly what Voyager discovered at the edge of the solar system, one must first understand one fundamental thing. Our sun is not just a bright ball hanging in the void. It is an engine, a colossal machine that continuously, every second, every moment of its existence, ejects flows of matter into space. And these flows shape everything we call home, the solar wind. The name itself sounds almost poetic, almost harmless. Wind, a light breeze, but behind this poetry lies a monstrous force. Every second, the sun loses about 1.5 million tons of matter. Not kilograms, tons. 1,500,000 tons of matter that breaks away from the solar corona and rushes away at a speed of 300 to 800 kilometers per second. During powerful coronal mass ejections, the speed reaches 2,000 to 3,000 kilometers per second. This is a stream of protons, electrons, alpha particles, helium nuclei, and heavier ions that rushes through space, filling it, piercing it, saturating it with the presence of our star. And this stream creates a bubble. Imagine it this way. Take a balloon and start inflating it. But you are inflating it not in a void, but in water. Air presses from the inside, water presses from the outside. And somewhere between them, a balance is established. The shape of the balloon is determined by the equilibrium of two forces, the air pressure and the water pressure. This is exactly how the heliosphere works. The solar wind is the air inside the balloon. The interstellar medium is the water outside. And the boundary between them, the heliopause, is the surface of the balloon. But unlike a balloon, the heliosphere is not round. It is asymmetric. The solar system moves through the interstellar medium at a speed of about 26 kilometers per second, approximately 93,000 kilometers per hour in the direction of the constellation Hercules. And this movement deforms the bubble. On the side where we are flying, the heliosphere is compressed. The pressure of the oncoming interstellar medium is stronger. On the opposite side, it is stretched, forming a long tail similar to a comet's. For many years, scientists argued about the shape of the heliosphere. Some believed it looked like a comet with a blunt nose and a long tail. Others suggested it was more spherical, almost round. A third group, and this is the freshest hypothesis, suggested that the heliosphere has the shape of a croissant. Yes, exactly. A croissant with two protruding jets at the poles and a flattened body in the equatorial plane. This model, proposed by Merav Ofer from Boston University in 2020, still causes heated debates. But whatever shape the heliosphere has, one thing is certain: it has an edge. And Voyager found this edge. Now, let's break down the anatomy of this edge layer by layer, because it is not one boundary, but several nested within each other, like Russian dolls. The first layer is the termination shock boundary. This is the point where the solar wind, flying at huge speed, suddenly slows down. Why? Because ahead is the interstellar medium, which will not let it through. The solar wind hits resistance and sharply brakes from supersonic speed to subsonic. It is here that the first hit occurs, the first contact with the wall. Voyager 1 crossed this boundary in December 2004 at a distance of 94 astronomical units from the Sun. Voyager 2 in August 2007 at a distance of 84 astronomical units. And here is the first mystery. The distances are different. 10 astronomical units of difference is 1.5 billion kilometers. The heliosphere is asymmetric. We knew that. But such a spread surprised scientists. It means that the shape of the bubble is much more complex and variable than thought. Moreover, Voyager 1 recorded that the termination shock boundary was fuzzy. The craft crossed it not once, but several times. The boundary pulsed, moved forward and backward as if it were breathing. The solar wind intensified, the boundary moved further. It weakened, the boundary approached. This meant that our protective bubble was alive. It reacts to every breath of the sun, to every flare, to every cycle of activity. Beyond the termination shock boundary begins the second layer, the heliosheath. This is a zone of chaos, a zone where the slowed-down solar wind collides with the interstellar medium and forms a turbulent, glowing, magnetically mixed region. It was here that Voyager discovered things that made physicists clutch their heads. Let's start with magnetic bubbles. In 2011, shortly before crossing the heliopause, Voyager 1 recorded that the magnetic field in the heliosheath was not smooth or directional, but broken into thousands of individual bubbles. Each bubble is approximately 160 million kilometers in diameter, which is comparable to the distance from the Earth to the Sun. The magnetic field inside each bubble differs from its neighbor in direction and strength. The entire heliosheath turned out to be like foam, cosmic foam of magnetic fields. No one predicted this. No model suggested that the edge of the solar system is filled with magnetic foam. And to this day, there is no universally accepted explanation of how it forms and what role it plays. One hypothesis is that bubbles arise due to magnetic reconnection instability when magnetic field lines break and reconnect, releasing a huge amount of energy. But this is only a hypothesis. Now let's move to the third layer, the heliopause. This is the formal boundary of the heliosphere, the point where the solar wind pressure exactly balances the pressure of the interstellar medium. Beyond it lies the territory of the galaxy. And it was exactly here that Voyager found the wall. When Voyager 1 crossed the heliopause in August 2012, the instruments recorded a sharp, dramatic transition. In a matter of days, the intensity of galactic cosmic rays jumped by an order of magnitude, and the intensity of solar wind particles fell practically to zero. The magnetic field changed direction. The density of the environment grew in a jump. But the most amazing thing is what happened after. Scientists expected that after crossing the heliopause, Voyager would find itself in calm, homogeneous interstellar space. A quiet harbor, a vast void with constant characteristics, a steady flow of galactic cosmic rays, a stable magnetic field, predictable density. Nothing of the sort happened. Instead of calm, Voyager discovered another zone of turbulence. The plasma density fluctuated. The magnetic field remained unstable. And what is strangest, it did not turn in the direction that the models predicted. If the interstellar magnetic field is determined by the structure of our part of the galaxy, its direction should have been specific. But Voyager showed a different direction, as if the craft had entered not open space, but another structured layer, another shell, another wall. And here we come to the key discovery, which was published in the journal Nature Astronomy and caused a shock in the scientific community. Voyager 1 recorded a steady, unceasing hum of plasma, a monotonous, low-frequency signal that did not interrupt for months. This hum had a frequency of about 3 kilohertz. If it could be translated into audible sound, it would resemble a quiet, even buzzing. But it is not the frequency that is important. It is important that by the characteristics of this hum, scientists were able to determine the density of the interstellar plasma, and it turned out to be abnormally high. Think about it. A craft located outside our stellar cocoon hears a hum, a continuous, even hum of interstellar space, as if the very fabric of the galaxy vibrates at a certain frequency, as if the space around our solar system is filled not with a void, but with something that sounds, something that trembles, something alive. This hum was recorded by the plasma wave instrument on board Voyager 1 in the period from 2017 to 2020. It continued continuously for almost 3 years, with small variations related to individual events, flares, which scientists interpreted as shock waves from solar ejections that caught up with the craft even at such an incredible distance. Now let's put all the puzzle pieces together. First, at the edge of the solar system, there exists a multi-layered structure of magnetic fields, plasma, and charged particles. It is not amorphous or blurred. It has clear boundaries and pronounced layers. Second, the density of the interstellar medium immediately beyond the heliopause turned out to be significantly higher than predictions and continues to grow as one moves away from the sun. Third, the temperature in this zone is abnormally high, tens of thousands of degrees. The energy that maintains this temperature has no obvious source. Fourth, the magnetic field beyond the heliopause does not match the models and points to the presence of additional structures we did not know about. Fifth, interstellar space sounds. It is filled with continuous plasma vibration, which indicates a dense, dynamic environment. All this together paints a picture completely different from the one we have painted for ourselves for decades. We are not surrounded by a void. We are surrounded by a wall, a dense, hot, structured wall of interstellar matter that compresses our heliosphere from all sides. This wall is not a passive barrier. It is active, it presses, it shapes. But where does it come from? What creates it? To answer this question, one must look even higher. Look at our solar system not from the inside, but from the outside. Look at it through the eyes of the galaxy. Our sun is located in the Orion Arm, a relatively small branch between the Perseus Arm and the Sagittarius Arm of the Milky Way. We are at a distance of approximately 26,000 light-years from the center of the galaxy. Our star makes one revolution around the galactic center in approximately 225 to 250 million years. This is called a galactic year. And here is what is important. Our solar system does not stand still. It rushes through the galaxy at a speed of about 220 kilometers per second relative to the galactic center. But relative to the nearest stars and the interstellar medium, our speed is those same 26 kilometers per second. And at this speed, we carve a path through the interstellar matter like a ship through water. And here the most interesting part begins. For the last few million years, the solar system has been moving through a region that astronomers call the local bubble. This is a giant cavity in the interstellar medium, an area with very low gas density spanning about 300 light-years. It is believed that the local bubble was created by a series of supernova explosions that occurred 10 to 20 million years ago. These explosions swept away the surrounding gas and dust, leaving behind a hot, rarefied cavity. Inside the local bubble, our solar system passes through an even smaller structure, the local interstellar cloud. This is a small, relatively dense cloud of gas and dust, about 30 light-years across, through which the sun is moving right now. And it is the matter of this cloud that forms the wall Voyager discovered. But here a problem arises, a serious problem. The local interstellar cloud has a temperature of about 6,700 degrees. That is approximately the same as on the surface of the sun. At such a temperature, the cloud should dissipate, scatter in all directions. Gas at 6,700 degrees cannot be held together by simple gravitational attraction. There is too little of it for that. The thermal motion of atoms should tear the cloud apart in a few thousand years. But the cloud exists. It is whole. It has not scattered. It is millions of years old, and it is still here. What holds it together? Scientists suggest that the cloud is compressed by external pressure, the pressure of the hot gas of the local bubble, which surrounds it on all sides. The local bubble has a temperature of about 1,000,000 degrees. This is residual heat from those same supernova explosions. This hot, rarefied gas presses on the denser and colder local interstellar cloud, preventing it from expanding. And so we get a picture. Our solar system floats inside a cloud, which itself floats inside a bubble, which itself is inside a galactic arm, which itself rotates around the center of the galaxy. Layer by layer, shell by shell, a bubble inside a cloud inside a bubble. And at every boundary, at every junction, there is collision, pressure, a wall. Voyager found the wall closest to us, the boundary between the heliosphere and the local interstellar cloud. But beyond it is another wall, the boundary of the cloud itself, where it meets the hot gas of the local bubble. And beyond that is another one, where the local bubble transitions into the normal interstellar medium. And beyond those are the walls of the galactic arms, and beyond them, the boundaries of the galaxy itself, where it hits the intergalactic medium. Walls are everywhere, on all scales. Space is not a void with patches of matter. It is a Russian doll of bubbles, each of which is limited by a wall of gas, plasma, and magnetic fields. And we live in the very center of one of these dolls, protected by the thin cocoon of the solar wind from the fury of the interstellar medium. But here is what does not give scientists peace. Voyager data shows that even after crossing the heliopause, even after exiting the heliosphere, the interstellar medium continues to surprise. The magnetic field beyond the heliopause turned out to be approximately 2 to 3 times stronger than models predicted, and its direction differs from the predicted one by about 20 to 30 degrees. This might seem like a trifle. So what? 20 degrees. But in astrophysics, such a discrepancy is a catastrophe for a model. It means that we fundamentally, incorrectly understand the structure of the magnetic field in our part of the galaxy. And the magnetic field is not just an abstract line on a map. It determines how cosmic rays move, how gas is distributed, how stars form, how the galaxy itself evolves. If our magnetic field models are wrong, then everything that follows from them is wrong too. It means we do not understand how cosmic rays penetrate the heliosphere, do not understand what radiation level actually affects the Earth, do not understand how reliable our shield is. And here is another detail that worsens the mystery. Voyager 2, crossing the heliopause 6 years later and in a different place, discovered that the boundary with the interstellar medium in its area was substantially different. The magnetic field had a different structure, the transition density was different, the temperature was different. This means that the wall around our solar system is not uniform. It has different thicknesses in different places, different temperatures, different densities. It is not smooth, but bumpy, uneven, torn, as if our cocoon were wrapped not in silk, but in crumpled foil. And here is the main question that science cannot yet answer. If the interstellar medium presses on our heliosphere with different strength in different places, can it at some point press all the way through? Can the wall on the outside turn out to be stronger than the bubble on the inside? The sun is not eternal. Its activity is cyclic. Every 11 years it passes through a maximum and minimum of activity. In the minimum, the solar wind weakens and the heliosphere shrinks. In the maximum, it expands. But this cycle is just a small oscillation. There are longer trends, and there are moments when the solar system passes through particularly dense clouds of interstellar gas. Paleoclimatic data recorded in Antarctic ice cores and ocean sediments testify that the level of cosmic radiation on Earth changed significantly over millions of years. There were periods when it increased several times. Some scientists link these jumps exactly to the passage of the solar system through dense clouds of interstellar gas, which compress the heliosphere and let more galactic cosmic rays through to Earth. And cosmic rays are not a harmless background. These are atomic nuclei accelerated to near-light speeds that pierce the atmosphere, damage DNA, cause mutations, and affect cloud formation and climate. An increase in the flow of cosmic rays can launch a chain of events leading to mass extinctions. Now about this we will talk in more detail later. Now it is important to fix the main point. The wall at the edge of the solar system is not a metaphor. It is a physical, measurable, real object. A multi-layered structure of interstellar plasma, magnetic fields, and flows of charged particles that surrounds our heliosphere and determines the very shape of our cosmic home. Voyager discovered it, measured its parameters, and transmitted the data to Earth. And this data showed that we know much less about the edges of our world than we thought. Science stands before a wall in the literal and figurative sense. Instruments record anomalies that do not fit into existing theories. Models require revision, textbooks, rewriting, and the only source of new data is two tiny crafts that have maybe 5, maybe 10 years left to live before their radioisotope generators finally run out and Voyager's voice falls silent forever. By 2030, according to NASA engineers' estimates, so little energy will remain on board Voyager 1 that the last scientific instruments will have to be turned off. The craft will continue to fly. Nothing will stop it in a vacuum, but it will fall silent, stop transmitting data, stop whispering, and become just a piece of metal rushing through the interstellar darkness. And after that, we will not have a single instrument outside the heliosphere, not a single eye on the edge, not a single ear listening to the hum of the wall, unless, of course, we send a new mission. But until the next planned interstellar mission, if it is approved and funded at all, decades will pass. And until the moment a new craft reaches the heliopause, more decades will pass. We may find ourselves in a situation where for 50 or more years we will have no information about what is happening at the edge of our world. 50 years of blindness, 50 years of ignorance, 50 years during which the wall will exist, press, pulse, and we will know nothing about it. And this is perhaps the most frightening aspect of this whole story. Not the wall itself, but that we have only just begun to see it and are already losing the opportunity to observe it. But while Voyager is still alive, while it still whispers, its whisper tells us about things we did not even imagine, about specific events, about specific anomalies, about cases where the wall manifested itself in all its power. And it is to these events that we turn next, to specific moments when Voyager's instruments recorded something so strange that scientists could not believe their own data for weeks, to cases where the wall did not just exist, but acted. There is a specific date worth remembering, August 25th, 2012. On this day, Voyager 1 officially left the solar system. At least, that was announced later, after months of data analysis. But in reality, everything turned out to be much more complicated than a simple crossing of a line on a map. And it is in the details of this transition that one of the most inexplicable anomalies ever recorded by human instruments is hidden. A few months before the final exit beyond the heliopause, Voyager 1 began to record strange events that scientists called magnetic highways. These were brief episodes when the flow of charged particles of solar origin sharply fell, while the flow of galactic cosmic rays just as sharply rose, as if someone momentarily opened a door in the wall, allowing galactic rays to pour in and solar particles to escape. And then, the door slammed shut. This happened many times. In July 2012, the craft recorded several such events with an interval of days. The flow of galactic rays jumped by 20 to 30% and then fell again. Solar particles behaved mirror-like, disappearing and appearing again. The magnetic field at the same time did not change substantially, which was particularly strange. If the craft were simply crossing a boundary, the magnetic field should have changed, but it remained as before, as if the wall let particles through but not fields, as if it were permeable for some and impermeable for others. Scientists from the Jet Propulsion Laboratory in Pasadena spent weeks trying to explain this phenomenon. Edward Stone, the steadfast project leader of Voyager for decades, publicly admitted that the observed data did not fit into any existing model. "Nature is telling us that we don't understand something," he said at a press conference. This phrase, spoken by one of NASA's most respected scientists, became perhaps the most accurate description of what was happening at the edge of the solar system. Then, on August 25th, everything changed finally. The flow of solar particles fell to zero, not to a low level, to zero. It completely disappeared. Simultaneously, the flow of galactic cosmic rays jumped to maximum values and stabilized. The craft went beyond the wall, found itself on the other side, but even after the exit, the oddities did not stop. On the contrary, they intensified. In October and November 2013, Voyager 1 recorded a powerful burst of plasma oscillations. The instruments showed a sharp increase in the density of the surrounding plasma. Scientists were able to determine that this was a shock wave, the trail of a powerful coronal mass ejection from the sun that occurred more than a year ago. Imagine the scale. The sun ejected a cloud of charged particles. This cloud flew for more than a year, covered 20 billion kilometers, broke through the heliopause, and overtook Voyager already in interstellar space. And when this shock wave reached the craft, it allowed scientists for the first time to directly measure the density of the interstellar plasma. The result, 0.08 electrons per cubic centimeter. This was significantly more than most models predicted. But the story did not end there. In 2014, another burst, another shock wave from the sun, and another measurement of density. This time, 0.10 electrons per cubic centimeter, higher than the previous time. The craft was moving away from the sun, and the density of the environment around it grew. In 2017, a new burst, the third in a row. Density, 0.13 electrons per cubic centimeter, even higher. The trend was confirmed. The further from the sun, the denser the medium. This completely contradicted simplest logic. In space, it should be empty, and the further from the star, the emptier. But reality showed the opposite. And then that same continuous hum we mentioned earlier was discovered. Between individual bursts caused by solar shock waves, Voyager 1 recorded a constant monotonous plasma signal, a steady vibration lasting without interruption from 2017 to 2020. And this hum gave another density measurement, 0.04 electrons per cubic centimeter. This is the background density on which individual bursts from shock waves are superimposed. Stella Koch-Ocker, a doctoral student at Cornell University who led the analysis of this data, published the results in 2021 in the journal Nature Astronomy. Her conclusion was unambiguous. The interstellar medium near the heliopause is substantially denser and more active than thought. The space beyond the wall is not quiet and not empty. It hums, vibrates, pulses. But let's move to Voyager 2, because its story adds completely new colors to this picture. Voyager 2 crossed the heliopause on November 5, 2018, at a distance of 119 astronomical units from the Sun. 2 astronomical units closer than Voyager 1. This meant that in the direction where Voyager 2 was flying, the heliosphere was slightly compressed. The wall on the outside pressed a bit harder. But the main advantage of Voyager 2 was something else. On its board, an instrument was working that had not functioned on Voyager 1 for 38 years. The plasma spectrometer. This instrument could directly measure the temperature, density, and speed of plasma ions, and its data turned out to be priceless. Voyager 2 showed that the transition through the heliopause was incredibly sharp. The thickness of the transition zone, the distance over which the environment parameters changed from solar to interstellar, was less than 1 astronomical unit, less than 150 million kilometers. On the scale of the solar system, this is the thinnest film, the thinnest membrane, a wall. Moreover, Voyager 2 discovered something that was not in Voyager 1's data at all. Immediately before the heliopause, in the last layer of the heliosheath, the craft recorded a layer of glowing plasma with a temperature of about 30 to 50,000 degrees. This layer was relatively thin but incredibly hot. Scientists called it the plasma barrier. It represented a zone where the solar plasma was heated to extreme temperatures immediately before contact with the interstellar medium. Where does this energy come from? How does plasma, which should cool as it moves away from the sun, suddenly heat up to tens of thousands of degrees at the very edge? One hypothesis is magnetic reconnection. When the magnetic lines of the solar field collide with the magnetic lines of the interstellar field, they can break and rearrange, releasing colossal energy. This energy heats the plasma, turning the thin boundary between our space and foreign space into a glowing, bubbling barrier. The wall does not just exist, it burns. Now let's add another layer to this story. Voyager 2 also discovered that beyond the heliopause, there exists a transition zone where the sun's influence is still felt. This is not pure interstellar space. The sun's magnetic field still penetrates beyond the boundary, though weakened. Solar particles still seep through the wall, though in negligible quantities. The boundary is not absolute. It is permeable. It breathes. It flows. And here we begin to approach a topic that changes the scale of our conversation, from the physics of a specific wall at a specific distance to processes of colossal power and destructive force that this wall holds back or does not hold back. Because the wall at the edge of the solar system is not just an interesting physical anomaly, it is a front line. It is a place where our star leads a continuous war with the galaxy. And the stakes in this war are life on Earth. Every second, a stream of galactic cosmic rays hits the heliosphere. This is not just radiation. These are atomic nuclei, protons, helium nuclei, nuclei of carbon, iron, accelerated to speeds constituting 99% and more of the speed of light. The energy of a single proton of a galactic cosmic ray can reach incredible values. In 1991, the Fly's Eye detector in the state of Utah recorded a particle with an energy of about 320 exa-electron volts. This is energy comparable to the energy of a baseball flying at a speed of 100 kilometers per hour. All this energy in one single proton, in a particle that is trillions of times smaller than a baseball. Such particles are called ultra-high-energy cosmic rays, and they still remain one of the greatest mysteries of astrophysics. We do not know what accelerates them. We do not know where they fly from. We only know that they exist, and that they continuously bombard our heliosphere. The heliosphere deflects most of these particles. The sun's magnetic field, stretched by the solar wind for billions of kilometers, works like a giant electromagnetic shield. Charged particles of cosmic rays flying into the magnetic field begin to spiral, deviating from their original trajectories, losing energy. Many of them never reach the inner regions of the solar system. But not all. The most energetic particles break through the shield. They penetrate the magnetic foam of the heliosheath, pass through the inner heliosphere, and reach the Earth. Here they are met by another shield, the magnetic field of the Earth itself, the magnetosphere, and yet another, the atmosphere. But even after all these barriers, some cosmic rays reach the surface. We live under a continuous shower of high-energy particles that penetrate our bodies every second. On average, every square meter of the Earth's surface receives about 10,000 cosmic rays per second. Most of them are harmless. They pass through tissues without causing noticeable damage. But some hit a cell's DNA and damage it. Usually the cell recovers, sometimes not. Sometimes damage leads to mutation, and a mutation can lead to cancer. And now imagine that the wall at the edge of the solar system weakens, that the heliosphere shrinks, that the sun enters a period of prolonged minimum activity, and its wind can no longer push the interstellar medium as far as before. The wall outside presses harder, the shield is thinner, and the flow of cosmic rays reaching the Earth increases. This is not a hypothetical scenario. This has already happened many times. Geological data shows that over the last 500 million years, the intensity of cosmic rays on Earth has undergone significant fluctuations. The isotope beryllium-10, which forms in the atmosphere under the influence of cosmic rays and accumulates in ice cores and ocean sediments, is a kind of Geiger counter recording the history of cosmic irradiation for millions of years. And here is what it shows. There are periods lasting millions of years when the level of beryllium-10 in sediments sharply increases. These periods suspiciously coincide with several phenomena, with glacial epochs, with mass extinctions, and with moments when the solar system, according to calculations, passed through particularly dense regions of the interstellar medium or through the arms of the Milky Way. Nir Shaviv, an Israeli astrophysicist from the Hebrew University in Jerusalem, published a work in 2003 in which he showed a correlation between the solar system's passage through the spiral arms of the galaxy and glacial periods on Earth. His argument was simple and elegant. When we enter an arm of the galaxy, the density of the interstellar medium increases. The heliosphere shrinks. The flow of cosmic rays increases. Cosmic rays ionize molecules in the lower layers of the atmosphere, creating condensation nuclei for clouds. More clouds, more reflected sunlight, colder on the surface. An ice age. This is a beautiful theory, and it still remains debatable. Not all scientists agree with it, But the very idea that the wall at the edge of the solar system can directly affect the Earth's climate has stopped being fiction. It has become a working hypothesis that is checked, refined, and discussed at the most serious scientific conferences. And here we approach the turning point of our narrative, the point where the physics of a specific phenomenon, the wall at the edge of the solar system, begins to intertwine with something much larger, with processes capable of destroying worlds, with events that go beyond our solar system and span the entire galaxy. Because the wall that Voyager discovered is only a specific case. One specific boundary around one specific star. But in our galaxy, there are 400 billion stars, and each of them has its own heliosphere, its own bubble, its own wall, and some of these walls are collapsing. When a massive star, 10, 20, 50 times heavier than the Sun, exhausts its fuel, it explodes as a supernova. Within a few seconds, energy is released equal to the energy the Sun will radiate for its entire existence, for 10 billion years. The shock wave from this explosion sweeps away everything in its path for a distance of tens of light years. It destroys the heliospheres of neighboring stars, exposing their planets to a flow of high-energy radiation. It compresses the interstellar gas to incredible density, generating new walls, new barriers, new structures. The local bubble inside which our solar system is located is the trace of one such explosion or several. About 10 million years ago, a series of supernovas knocked out a giant cavity in the interstellar medium. Gas and dust were crushed, heated to 1,000,000 degrees, and ejected for hundreds of light years. And in this void, we now live. But here is what makes one think. If the local bubble was created by supernova explosions, it means our solar system experienced the consequences of these explosions. Shock waves reached us. The heliosphere was compressed, the flow of cosmic rays increased. The radiation background on the Earth's surface rose. And indeed, in 2020, a group of scientists discovered an increased concentration of the isotope iron-60 on the bottom of the Pacific Ocean, a radioactive isotope that does not form on Earth, but can reach us only from space, from the remains of a supernova explosion. The age of these sediments is from 2 to 3 million years. This means that about 2 to 3 million years ago, supernova debris, real physical particles from the explosion of a dying star, fell on our planet, reached the bottom of the ocean, lay in the ground, and we found them. The distance to this supernova is estimated at approximately 150 to 300 light years. Far enough so the explosion would not destroy life, but close enough for its consequences to be measurable. Close enough so that the wall around our solar system would shudder. And what if the supernova were closer? Say 30 light years away, or 10. At a distance of 30 light years, a supernova explosion is capable of destroying a significant part of the Earth's ozone layer. The sun's ultraviolet radiation, which is usually blocked by ozone, will pour onto the surface. Plants will die, food chains will collapse. Mass extinction. At a distance of 10 light years, the consequences will be catastrophic. Gamma radiation from the explosion will reach the Earth in 10 years and hit the atmosphere. The ozone layer will be completely destroyed. The planet's surface will be sterilized by radiation. Only organisms living deep in the ocean or underground will survive. And the wall at the edge of the solar system will not help. The heliosphere is not capable of stopping gamma radiation. It protects against charged particles, against cosmic rays, but not against electromagnetic radiation. Light, even deadly light, will reach through any wall. For it, there are no barriers. We are approaching the darkest part of this story, to the realization that the wall at the edge of the solar system is simultaneously both protection and a prison. It separates us from the galaxy but cannot protect us from everything. It gives an illusion of safety, but beyond it rage forces we are only beginning to understand. And every day, every hour, every second, Voyager continues to fly through this wall, going further into interstellar space, measuring, recording, transmitting. And every bit of data it sends makes the picture simultaneously clearer and more frightening. The wall is real. It is hot, it is dense, it is non-homogeneous, it pulses, and behind it is not void. Behind it is a battlefield where forces collide that are capable of destroying civilizations. There is one thought that does not let go after everything we have learned. A simple thought, but it takes your breath away. We live inside a bubble. This bubble is the only thing that separates us from infinity. And this bubble is temporary. It will not exist forever. Nothing will exist forever. Neither the sun, nor the heliosphere, nor the wall that surrounds us. And now, when we have realized the scale of the physical processes occurring at the edge of our world, the time has come to ask questions that go beyond physics. Questions that concern not atoms and magnetic fields, but ourselves, our place in the universe, our meaning, our future. What does the existence of the wall mean for humanity? Let's start with the most obvious. The wall at the edge of the solar system is the border of our home, but it is also the border of our prison. We are locked inside, not physically locked. Theoretically, we can send a craft through the wall, and Voyager proved it, but practically locked, because between us and the nearest star is not just distance. Between us and the nearest star is a wall. Our wall, which must be overcome on the way out, and a foreign wall, which must be entered on the way in. Proxima Centauri, the star closest to us, is at a distance of 4.24 light-years. That is 40 trillion kilometers. At Voyager's speed of 17 kilometers per second, the journey will take more than 70,000 years. But even if we could fly 100 times faster, 1,000 times faster, we would still have to break through the wall on the way out of the solar system and enter the wall on the approach to Proxima. And every star in the galaxy is surrounded by its own heliosphere, its own bubble, its own wall. The galaxy is not a void with a scattering of stars. It is a sea of bubbles, each of which is separated from the neighbor by a barrier of glowing plasma, magnetic fields, and cosmic rays. And between these bubbles, the interstellar medium is also not empty, also filled with matter, also dangerous. A journey to the stars is not just overcoming distance, it is overcoming a series of walls. And each wall is a challenge we do not yet know how to accept. But there is another aspect of this problem, deeper, more disturbing. If our solar system is surrounded by a wall that protects us from galactic radiation, then what happens to planets that lack such protection? Not all stars create heliospheres. Red dwarfs, the most common stars in the galaxy, making up about 70% of all stars, have a much weaker stellar wind than the Sun. Their heliospheres, if they exist at all, are significantly smaller and weaker. Planets around red dwarfs can find themselves practically without protection, completely exposed to the flow of galactic cosmic rays. Proxima Centauri is a red dwarf. It has a planet in the habitable zone, Proxima b. This planet is close enough to the star so that liquid water could exist on it, but it is also close enough to receive powerful flares of radiation from the star itself. And Proxima's stellar wind is too weak to create a full-fledged protective bubble. Astronomers from Villanova University published a study in 2017 showing that Proxima b is subjected to radiation flares hundreds of times, exceeding any flares the Earth ever received from the Sun. If an atmosphere ever existed on this planet, it is likely long since stripped away. If there was once life there, it is likely long since destroyed. And there are billions of such planets in the galaxy. Billions of worlds that theoretically could be habitable, but are deprived of the protection our heliosphere gives us. Billions of possible cradles of life that have become radiation deserts because they were not lucky enough to be born next to the right star. And here we approach one of the greatest mysteries of space, to the question that has tormented scientists for more than half a century, to the Fermi paradox. If the universe is so huge, if there are hundreds of billions of galaxies in it, each with hundreds of billions of stars, many with planets, and some of these planets are inhabitable zones, then where are all the intelligent civilizations? Why do we not see their traces? Why is space silent? There are dozens of explanations for the Fermi paradox. Maybe intelligent life is incredibly rare. Maybe civilizations destroy themselves just after reaching technological maturity. Maybe they exist, but intentionally hide. Maybe we are just looking in the wrong place, listening with the wrong thing, searching the wrong way. But the wall at the edge of the solar system offers one more explanation. Simple and eerie. Maybe most planets on which life originates simply do not have protection. Maybe our solar system is a rare exception. Maybe the combination of factors that allowed life on Earth not only to arise but to develop for billions of years, this combination is so improbable that we may be alone. Not because life is rare, but because protection is rare. The sun is a star of the right type. Not too hot, not too cold, not too active, not too quiet. Powerful enough to create a vast heliosphere. Stable enough so that this heliosphere existed for billions of years without catastrophic fluctuations. Earth is a planet of the right size, large enough to hold an atmosphere and a magnetic field, small enough not to turn into a gas giant. Its magnetosphere is the second layer of protection after the heliosphere. The location of the solar system is right. We are between spiral arms in a relatively calm area of the galaxy, far from the center, where there is too much radiation from the supermassive black hole and star clusters. Far from regions of active star formation where supernovas explode. And the local bubble, the giant cavity in which we float, may also be a protection factor. Inside the bubble, the interstellar medium density is lower than outside. The wall around our heliosphere presses a bit weaker than it would in a denser environment. All this together, a cascade of improbable coincidences. And if even one link in this chain is broken, life may not survive, not develop, not reach intelligence. That is why space is silent. Not because there is no one there, but because few survive long enough to speak up. But this hypothesis generates an even deeper question. If our existence depends on the wall, then what will happen when the wall changes? And it will change. It is already changing every day. Solar activity is cyclic. Every 11 years we pass through a maximum and minimum. But there are also longer cycles. The Gleisberg cycle, about 80 to 90 years. The Suez cycle, about 200 years. And there are even longer periods that we are only beginning to understand by studying isotopes in ice cores and tree rings. In periods of solar activity minima, such as the Maunder minimum in the 17th century, when there were practically no spots on the sun for 70 years, the heliosphere shrinks, the wall outside presses harder, the flow of cosmic rays increases, the climate on Earth cools. The Maunder minimum coincided with the so-called Little Ice Age. Winters in Europe were harsh. The Thames froze, crops failed, hunger and diseases were rampant. We do not know for sure if the link between the minimum and the cold was cause and effect, but the coincidence is too precise to ignore. And now imagine a longer minimum or a deeper one. Imagine the sun entering a period of prolonged weakening for hundreds or thousands of years. The heliosphere shrinks radically, the wall moves closer to us. Cosmic rays lash through the weakened shield, mutations accumulate. Cancer becomes an epidemic. Cloud cover increases, temperature falls, glaciers advance. This is not a scenario from science fiction. This is one of the possibilities being actively discussed in the scientific community. And we do not know when or if this will happen. We have studied the sun too little to understand its long-term trends. Our direct observations span only a few centuries, a drop in the ocean of the 4-billion-year history of the star. But there is a scenario even more disturbing, related not to the weakening of the sun, but to a change in our environment. The solar system moves. It rushes through the galaxy at a speed of more than 200 kilometers per second, and on its path, it encounters different sections of the interstellar medium, sometimes rarefied, sometimes dense. Right now, we are at the edge of the local interstellar cloud. Some models predict that within the next few thousand years, possibly even a few centuries, we will exit this cloud and enter a neighboring structure. This neighboring structure may be denser or less dense. We do not know. If it turns out to be denser, the pressure on the heliosphere will increase, our protective bubble will shrink, the wall will move closer. The consequences may be similar to those caused by a solar activity minimum, but we will not be able to control them. This will be an external factor, cosmically independent of us. And now remember the supernovas. Explosions of massive stars can happen at any moment. In our galactic neighborhood, there are several candidates. Stars that are close to the end of their lives and may explode in the next thousands or millions of years. Betelgeuse in the constellation Orion is one of them. It is at a distance of about 700 light-years, so its explosion will not be catastrophic for Earth, but it will be spectacular. For a few weeks, a second moon will appear in the sky, a bright dot visible even during the day. But what if closer to us there is a star we do not know about? What if in some dense nebula hidden from our telescopes by dust, a massive giant is finishing its days, ready to explode at any moment? We cannot see everything. Our maps are not complete. Our knowledge is limited. And this is perhaps the most frightening thought of all. We live in a world that seems stable, predictable, safe to us. The sun rises every morning. The stars twinkle every night. The seasons change each other. But behind this illusion of stability hides chaos. Space is cruel. Space is indifferent. Space can destroy everything dear to us, and we will not even have time to understand what happened. The wall at the edge of the solar system is a reminder of this, a reminder that we are not masters of the universe. We are not even guests. We are a tiny fluctuation in the vast ocean of energy and matter that by some miracle learned to realize itself. And yet we are here. We survived 4 billion years of evolution through all catastrophes, all extinctions, all cosmic hits. And we are here. We built a civilization. We created technologies. We launched into Voyager a small piece of metal and silicon that reached the edge of the solar system and sent us word. And this word, for all its frightening nature, also contains hope. Because now we know. We know that the wall exists. We know what it consists of. We know how it works. This knowledge is power. This knowledge allows us to prepare, plan, dream. Someday, in 100 years, in 1,000, in 10,000, humanity may learn to leave the heliosphere not as a timid probe, but as a full-fledged ship. We can learn to break through the wall and exit into interstellar space. We can find ways to protect ourselves from cosmic radiation, build our own artificial heliospheres around our ships. We can become an interstellar species, and then the wall will stop being a border. It will become a threshold, a door beyond which an endless journey begins. But this is the future. Distant, uncertain, possible. And what about now? Now Voyager 1 is at a distance of more than 160 astronomical units from the Sun and continues to move away at a speed of about 3.5 astronomical units per year. Every day it covers about 1.5 million kilometers, going deeper into interstellar space. Every day it measures the plasma around it, records magnetic fields, counts cosmic rays. Every day it whispers its 23 watts into the abyss, and this whisper reaches us in 22 hours, bringing new data, new riddles, new answers. Its plutonium generator is weakening. Every year it loses about 4 watts of power due to the natural decay of the fuel. Now the generator produces about 250 watts, less than half of the initial power. By 2025, the energy may become too little to maintain all the instruments. Engineers will have to choose which to turn off. By 2035, the craft will likely fall silent completely, and then silence will come. Voyager 2 is another hope. It is younger than its twin. Its generator is slightly more powerful. It may last a few years longer, but it too will fall silent. Sooner or later, both crafts will become dead bodies rushing through the interstellar void without a single signal, without a single measurement, without a single thought. But they will continue to exist. Metal does not rot in a vacuum. Plastic does not decompose. The golden records with recordings of human music and voices attached to the side of each Voyager will fly through the galaxy for billions of years more. They will outlive the sun. They will outlive the Earth. They may become the last thing left of humanity when our civilization disappears, as all civilizations before us disappeared. And maybe, just maybe, in millions or billions of years, one of the Voyagers will be found, picked up by some being or machine we cannot even dream of, and then the golden record will be played. And someone's mind, not at all like ours, will hear a greeting in 55 languages, hear the music of Bach and Beethoven, hear children's laughter and a newborn's cry. It will hear the sound of footsteps and the noise of the wind, hear us and understand that once, very long ago, on a small planet near an unremarkable star, there existed a species that looked at the stars and asked questions, that tried to understand, that sent a message in a bottle across the cosmic ocean, not knowing if it would ever reach the shore. This is what the wall at the edge of the solar system is. It is not just a physical phenomenon, it is a mirror in which we see ourselves, our fragility, our courage, our loneliness, and our hope. We are surrounded by walls, the wall of the heliosphere, the wall of distances, the wall of time, the wall of our own ignorance. But we break through these walls slowly, atom by atom, bit of data by bit, one small step at a time. We send probes, we build telescopes, we ask questions. Sometimes rarely, but delightfully, we get answers. Voyager reached the wall and told us about it. Now we know that it exists. Now we know what it looks like. And now we can think about how to overcome it. But for now, we are here, inside the bubble, protected by a thin film of solar wind from the fury of the galaxy. While we can look at the stars without burning from radiation. While we can breathe, love, dream, create. While the wall holds, close your eyes. Imagine yourself on board Voyager. You fly through absolute darkness, far from everything you ever knew. Behind is a tiny dot that was once your home. Ahead is infinity. Around is the hum of plasma, invisible but palpable. The vibration of space, the breath of the galaxy. You are alone, but you carry with you the memory of billions, the memory of everyone who ever lived, the memory of everyone who looked up and wondered. You are an ambassador. You are a witness. You are the last voice, and you fly endlessly through the wall, through the darkness, through time, towards something we cannot yet name. Maybe to other intelligences, maybe to the void, maybe to a truth that will change everything. The wall at the edge of the solar system is real. Voyager found it, and now you know about it. What will you do with this knowledge? It is up to you. You can forget. You can remember. You can close your eyes and fall asleep, knowing that right now, at this very moment, a small craft weighing 800 kilograms is rushing through the interstellar gloom, carrying a part of you, a part of us all. Sweet dreams. May you dream of the stars,